All right, what's up, everybody? Welcome back to Structure Free Learning. And we're going to do an example problem here where we look at a rigid body that is undergoing plane motion, and given the velocity at one point, can we find the velocity of another point as well as the angular velocity of the rigid body? And there are two methods that we would use to do something like that. We would do a relative velocity analysis, which involves using a relative velocity equation, or we would use the method involving the instantaneous center of rotation, also known as the instantaneous center of zero velocity. And in this problem, I've got like this ladder that's up against the side of a hill, and the angle here of the hill relative to the horizontal is 60 degrees right there. And this ladder is sliding down, it starts to slip. And I know that the velocity at point B here is 2 meters per second. And what I'd like to do, given that this velocity is 2 meters per second to the right, and the length of this ladder or this rod is 10 meters, can I find the velocity of point A and the angular velocity of this rod? I'll show the relative velocity approach as well as the instantaneous center approach. But this is what that schematic looks like right here. This is what the drawing is. And so the question right now is, what is happening at A? What is the velocity at A? And what is the angular velocity of AB? Here, the first thing I'm going to do, the first way I'm going to say part A is I'm going to use the relative velocity approach. So when I do the relative velocity approach, what I would do is essentially the equation, the relative velocity equation is this VA is equal to VB plus the velocity of A with respect to B. This relative velocity equation is something you learned at the very beginning of particle kinematics, and now we're going to apply it for rigid body plane motion. We're going to have a schematic that reflects each part of the equation. So I believe the first thing that I'm going to do is draw a schematic. I'm going to draw 3 sticks essentially that look like this. And what I'm drawing here is basically the ladder 3 times. Here, this is end A, this is end B. And what I know is that the velocity of B right here, this VB, is 2 meters per second to the right. I don't know VA. I can guess VA. I'll guess that VA, because of it leaning and sliding against the side of this wall, or this incline, I'm going to guess that VA is going to be going down. This will be my guess. It'll be going down the incline like this, but I don't know what its magnitude is. And so this is my plane motion side of the drawing. I'm going to apply one of the velocities, typically the known velocity, as a translation of the rigid body. So here, this middle drawing reflects pure translation. And what we're going to do is translate the rigid body according to point B. Every point on the rigid body will experience the same velocity for us, which in this case is VB. So VB is applied everywhere because we're breaking up this plane motion into a translation plus a rotation. And another way to look at it is as if when I apply this translation and I apply the translation according to the velocity at B, it's like I'm putting B to its final position. All right, so B is in its final position, and now I want to put a pin through point B, and this will become, because B is in its final position, this will become the axis of rotation. Now that B is in its final spot, I just need to rotate the structure or rotate the system so that I can get A to its final spot. And so I'm going to guess an angular velocity direction for this, and I'm going to assume that the angular velocity is going clockwise omega AB. You can guess the other way and you'll just end up with a negative number. But the important point is that based on your guess for this angular velocity omega AB, the velocity of A with respect to point B is corresponding with omega AB. So that means means that my tangential direction is 90 degrees like this, and my corresponding velocity would be in rotation, would be here. This would be VA with respect to B like this. All right. The basic idea of the schematic is we take this plane motion, break it up into a translation plus the rotation. The translation I apply is the known velocity. Until you get really good at it, I would just recommend that you keep applying the known velocity as your translation. And then I put a pin through the point that I used as part of my translation. So in this case, B, which is in its final resting spot. And I put a pin through there. That becomes my axis of rotation. I guess a direction for the angular velocity, omega AB. And then I draw the corresponding velocity or relative velocity vector, VAB. And if you can tell, my equation here will reflect point A, and we're focusing on this point A here as part of my relative velocity equation. So I'm going to focus on that point, and this will be VA is equal to VB plus VAB. To solve this problem, I'm going to break this up into components. And so I'm going to look at the horizontal component, and I'm going to look at the vertical component like this. And so if I do some work here, according to my drawing here, my velocity of A, my guess is that it's going down the ramp or the incline like this. And so based on this 60-degree angle, I know that here, this angle relative to the horizontal is 60 degrees like this. And so I know that my horizontal component, if I'm choosing positive to the right, this will be VA cosine of 60 degrees is equal to, let's see, I have a velocity of B applied there. And so this will just be straight up VB plus, well, I'm going to need an angle here. I'll call this angle theta. And that angle right there will be VAB cosine of theta. And then in the vertical direction, I would have negative VA sine of 60 degrees is equal to, well, B does not have a vertical component, so 0. And then based on my drawing here, this would be positive VAB sine of theta right here. And the beauty of this rotation analysis here is that, well, shoot, the magnitude of VAB is my basic rotation equation, which would be that the angular velocity AB times the distance from B to A, this distance right here, RBA, which is just 10 meters. This is 10 meters. So here this would be RBA, and that's known. And so it's the magnitude of this velocity is just omega times RBA. And so if I make that substitution here, and right now I have one unknown. VA is an unknown. I know VB. VB is 2 meters per second to the right. I know RBA is 10 meters. And let's see, omega AB is an unknown. So I'll circle that. And then the theta. This angle is an unknown. And so, man, I got to do some work and figure out what this angle theta is. And if I really think about it, well, let's see. I know that this angle right here, there's maybe this angle, if I call that phi, this will be the angle phi like that. Okay, and then I'll have that angle theta. And I know phi plus theta is 90. So if I can get phi, then I can get theta. And so if I look back here, well, shoot, AB is right here. This is my angle phi that I'm looking at. And, oh, there is one more bit of information that I didn't give you, but this distance right here, this is 4 meters. Very important right there, that distance. And so we can, let's see, based on this triangle that I see, so here I can make a better drawing of this triangle. So here is my triangle. This side right here is 10 meters. I know that this angle right here is 60 degrees. And basically by one line right here, I know this angle right here is 120 degrees. right here. So I have this, and I know the length of this side right here is 4 meters, like this. I can use the law of sines to figure out what this angle is, as well as this angle right here, which we have called phi. Right there. I'll call it gamma. All right. And so from the law of sines, I would say the sine of gamma over 4 meters is equal to the sine of 120 degrees over 10 meters. And if I do some math here, I will get that gamma, this angle is 20.27 degrees, like this. And then I know that gamma plus phi plus 120 should equal 180 degrees. And that will make this angle right here, let's see, 60 minus 20.27. And that would say that phi is 39.73 degrees right there. So I know that that angle phi is 39.73 degrees. In fact, I would probably call this step 3. And it's always working out some geometry. All right. And so now when we return here, looking at this, well, shoot, I know that phi is 39.73 degrees. And that would make theta, in this case, theta would be 90 minus 39.73 degrees, which is 50.27 degrees. Yes. All right. So we know what that theta is, this right here. And what I'm left with is time to just plug and chug or solve. Time to solve, and really, if you can see already, it's 2 equations, 2 unknowns, and I should be able to solve it out. So let me do that real quick. And we get omega AB is negative 0.185 radians per second, which means that negative sign is opposite of what I drew over here. So omega AB is actually 0.185 radians per second counterclockwise. And then if I plug and chug back into to this equation back here into 2, then I will get the velocity of A, 1.64 meters per second. We'll get a positive result indicating that that initial guess way back here, this guess of VA downwards, is correct. All right, so that's how you solve this using the relative velocity approach. Next up in part 2, we'll just do this exact same problem using the instantaneous center of rotation, or zero velocity, which you can go to by clicking right here. All right, talk to you soon. Structure free.